Our next presenter for today is Kevin Hiers, who'll be talking about prescribed fire science and will do a demonstration on BurnPro 3D. Kevin served in wildland fire-related leadership roles during his career at organizations including, but not limited to, Eglin Air Force Base, the Air Force Wildland Fire Branch, Tall Timbers Research Station, and the U.S. Geological Survey. He currently, and this is as of November 1st, serves as the Department of Defense's Resource Conservation Program Manager for the Strategic Environmental Research and Development Program, or what's known as SERDP, and the Environmental Security Technology Certification Program, or ESTCP. For more than 25 years, Kevin has worked at the interface between management and science. His program applies research to support the safe and effective use of prescribed fire through research on the interacting fire lines, fire atmospheric feedback, driving smoke transport, and mechanistic understanding of fire effects. He is one of the co-founders of the Prescribed Fire Science Consortium. And with that, I will turn it over to you, Kevin.
All right, James. So for the audience, I'm going to test out a live demo of part of the system, but given the bandwidth issues, this could go south pretty quick. And I'm going to rely on Casey Teskey to text me if I just need to go to the still shot backup PowerPoint. So just yell at me, Casey, if it doesn't look okay. For now, though, James, I do want to just confirm that you're seeing my my screen with BurnPro 3D app pulled up.
Yep, and it's nice and clear. So far, so good.
Well, as you've seen, in order to enable some of these next generation couple fire atmospheric modeling tools, we literally have had to assemble a team to change every aspect of the game. You know, so much of the wildland fire world has been built around, you know, sort of rapid prediction of sort of landscape scale fire behavior modeling and the reliance on empirical data maybe to predict fire effects. Whereas now we're trying to get into mechanistic fire behavior modeling that is physics-based, that has that we don't tune the model per se, but we might try to refine the inputs in order to improve prediction, and that, you know, creates an opportunity to learn from models in a more sophisticated way. Not saying that they're perfect, but to learn what we don't know. And I think that what this presentation really represents now, and hopefully the slides will show some of that. Is that, you know, we're really getting close to the point of being able to operationalize access to these, and at this point there's been quite a bit of information in our, you know, conversation in the chat, and we want to open it up afterwards. We want to engage managers early in this process. James emphasized the co-production. There are several managers on our team that have been helping us to develop, you know, an operational space for these new tools. But you know, we really all want to encourage you to reach out to us if you have interest, both in beta testing and providing just opinions as to whether you know, the user interface is of value, or whether you think the model's not underperforming or not performing properly in certain situations. And so that is why we're here, is not to show you a final product, but to invite you into a more robust discussion about how we create this together. And so, as Ilkay teed up, the BurnPro 3D app is one of those initial applications that we're trying to develop as a big team to take all of these data, three-dimensional high-resolution data sources that Russ mentioned, and these sophisticated models. Right now, we're going to be demoing BurnPro 3D with QuickFire, but there's other modeling tools out there, and Russ showed WFDS and Level Set as another example. And what to enable these for managers, but what the process of diving deep into the details, high temporal and spatial resolution, shows is we need to be thinking about how we plan burns to much greater detail. And so this app, hopefully you'll see, is designed around that. And so first of all, as Ilkay mentioned, we're sort of stitching together a number of tools to create this interface and enable the ensemble approach to fire behavior modeling, where we take, you know, a range of parameters and we plug them through a massive amount of computational resources and get outputs that hopefully allow us to develop some confidence around our burn prediction or prescribed fire planning predictions for burn managers. And this experience is really just going to follow a 5-step process of choosing a burn area, defining how you're going to import 3-dimensional fuels, defining ignition pattern. And we'll spend a little bit of time on this because this is what managers control the most once the match is struck. And then looking at how we can select environmental parameters for ensemble construction, and reviewing and finalizing the burn plan. And Ilkay mentioned that in order to really refine this approach, we've identified user personas, and this is a burn planner looking long-term, planning horizon, maybe a year out, several months out, thinking about a unit that may or may not have been burned before. And so in step 1, just selecting the burn area. Hopefully this is going to work live, and if it doesn't, Casey, just yell at me. We can go to places around the country. You can load up a shapefile of your burn unit. Here's one at Piedmont, one that Russ planned at the Willamette Valley. And being able to load these units up into the system should be easy, quick and easy. There's Russ's units off to the side. And then we've been working with Jen Anderson at Yosemite more closely to sort of develop this user interface. I want to emphasize that the model itself, what I'm demoing, is not about the model. We can talk about that afterwards, but really trying to think about how would a burn planner use these tools in order to develop a burn plan that meets objectives. And so to start with, you have to understand what objectives you want. Because we link mechanistic fire effects with hopefully a better prediction of refined fire behavior that is connected to your choice of ignition pattern, as managers, we want to start this process in the burn plan with measurable desired objectives. So we've got surface consumption. In this case, you can choose 60 to 90, mid-story consumption, and just run this up to whatever numbers you'd like. You can type them in if you don't want to click fast, but desired canopy consumption, and we might want to have something as little as 5 to 20%. What I would like to point out, especially as we get into interpreting ensembles, is in the interface, you can define what you consider mid-story fuel height and canopy fuel height. When Russ voxelizes in fast fuels, we're looking at 1 meter resolution. So in the vertical stack, it's very Minecrafty, but you can think about what you consider mid-story fuels and deciding how you want to represent your spatially explicit, high resolution measurable objectives for consumption. And so just very quickly, let me see, we're going to go back and so step 2 is identifying those 3-dimensional fuels. And I knew it was going to try to make me log in again, but that's okay, because we're going to have these pulled up. And here's within the Yosemite area that we've got, this is what the voxelized fuels look like. And I will just say that that we've chosen in the initial experience these little round balls. I prefer these, which are much finer resolution depiction of fuels, as squares and cubes, because that's really how fast fuels and our interpretation of LiDAR is representing them in the system. And so once you've selected your high resolution fuel layer, it's time to think about ignition patterns. And in this system, I think one of the most advanced, one of the funnest part of advancing these next generation fire behavior models, particularly for prescribed fire application, which is near and dear to my heart, is thinking about ignition pattern in a much more sophisticated way than we've ever been able to model before. And so we have in creating a new simulation in this new tool called Drip Torch, which Russ's team at Holtz Forestry developed for the Wi-Fi project, and that's Anthony Marcosi and Lucas Wells. This is a way for managers to input the ignition pattern that they want to use in order to light a real unit. First of all, I want to just point out that Drip Torch, based on the wind direction, here's 90 degrees, so it's coming out of the east. Drip Torch instantly just assumes that your black line operation was successful. And so we sort of remove fuels from whatever distance off of the fire line that you want us to do. And then it allows you to choose things like strip head fire, flanking fire, backing fire, ring fire. It looks at line continuity. Do you want to add dashes, which is what we have displayed here? What's the length of the dashes? What's the gap between? How many igniters do we want? And so, thinking about these tools, and particularly, drip torch as a way of igniting a fire in a realistic, manner to kickstart your ensembles automatically, to me, gives managers a lot more control over what they'd like to plan for under a variety of conditions. I am going to just kick over here and show, some strip head fire. You've got a lot of control here, and if I'm going to say increase the distance between to 50 meters. One of the things that that drip torch does reasonably well is that it tells you how long it's going to take to ignite that unit, because when you are specifying, you get to tell it how fast you walk. 3 miles an hour is faster than most folks walk. You'll notice these two lines are closer together. You get to specify the path distance. So when you maybe flip the grid after your, in this case, 5 igniters come through the unit, what if we wanted to increase that to 30 meters? Now you can see how the pattern has changed. And if we just want to keep it even, we can go to 50, and drip torch will define that ignition pattern based on your inputs. The exciting part about that is that then hopefully, you are returned an ensemble that is of model runs. In this case, here's a total of 100 simulations that define, that allow you to check out surface fuel consumption based on your objectives. You can also change your objectives. So in this case, we had specified, low canopy consumption. But if you remember in that initial screen, I defined mid-story as up to 6 meters. Well, this particular unit's got a lot of low-hanging branches. So some of those ladder fuels are being counted as canopy consumption. So if you are defining what the canopy is, now you might take into consideration, I can widen my prescription window and allow for 35% consumption, because what I expect is that consumption being lower crowns. We're just, we know that we can handle that. And you have the ability, once those ensembles are created, to go through all of your ensemble runs. And some of these runs, we've got thousands of runs, and to be able to explore space. If you're worried about the amount of crown fire outside the unit in some of these model runs, you can look at that. If you're really conservative, because quickfire in this case is just moving moisture off the unit based on pretty simple physics, you can look at what surface fuel moistures become available based on your allowable canopy consumption. And in a lot of cases, these prescribed fire is going to be very sensitive, to the surface fuel moisture, as well as the canopy fuel moisture specified through both fast fuels and BurnPro 3D. So in a sense, these ensembles really now represent what the most sophisticated models we have say is a range of possibilities based on your level of input. One of the things that I emphasized in the chat is right now the models also, in fact, this is the way that I like to think about them, give us as managers and scientists a chance to learn. What is the physics saying we're sensitive to? One of the things that recently we got feedback from managers is that the models were exceptionally sensitive to we're going to spin here. There we go. Exceptionally sensitive to the amount of energy that we were lighting each line with. And so now that we're thinking at meter scales, when we were putting the defaults into quickfire for the BurnPro 3D ensemble, we essentially, instead of lighting it with drip torch energy, we're lighting it with Alumagel energy. So in being able to back off of that, working with managers, maybe even to add, and this is what we concluded with John Wallace, adding the toggle. How much energy do you think that you're going to ignite with? If it's a ping pong ball from a drone or a helicopter, it's going to be much less than a drip torch. And if you've got access to a helicopter and you're going to be using Alumagel and a heli torch, you need to be able to add energy into each cell as you're igniting. And those have cascading and important consequences for how fire spreads and how you can meet objectives, particularly as you add more energy. Your prescription is going to open up on that high fuel moisture in. I'll just end very quickly with one of the exciting things that I feel like we've created. Now you can explore, once you have these ensembles, you can explore prescription space. You may have specified, these are my objectives and these are the conditions that I'd like to see tested. But as you get closer to the edge of fuel moisture or relative humidity and wind speed, you may want to be able to adjust your expectations for something like surface fuel consumption. And that will start to open up different parts of the ensemble. And you can see, as we allow canopy consumption, when we change canopy consumption here, we're going to open up some different windows, within the ensemble itself. And lastly, we do want to emphasize that each of these runs has a quick fire, model behind it. Quick fire does allow for fire to spot across lines based on energy deposition and the convective energy produced and wind, three-dimensional wind fields. These, though we're displaying fuel density for the surface fuel layer, are all three-dimensional runs on fast fuels. And you can run through your ensemble to see what kind of variation you expect based on the conditions. And, periodically, let's see if we get one of these wild ones, spreading under high wind scenario, you get to decide, well, maybe I'm getting too close to the edge of my comfort zone when I've got wind speed from this direction and fuel moisture of such amount. But I will just end with that. And actually, James, before I do it, maybe I'll tee this up. One of the exciting things that ties what Nick produced and what we're thinking about with these three-dimensional fuels is the ability to integrate terrestrial laser scanning as part of the modeling. And in Yosemite, we produced, and I'm just going to not show this in slideshow mode, my apologies. We used a small low-cost laser, BLK 360, to take fuel plots with managers and to look at fuel conditions. And Nick, mentioned that there's a lot of analysis going on behind the scenes that interprets these three-dimensional scans. But one of the exciting parts about the scans are the fact that they are photo points and they're embedded in time and space. And we are working on a database connection through the Wi-Fi Commons and USGS to be able to link up so that burn bosses, if they're burning in a unit or you're a burn planner and you're planning a unit, you can dive into these three-dimensional depictions of your units. This is one after a burn in New Jersey, so that you can actually visualize what your fuels are as you're setting up the ensemble runs for your particular unit. And with that, I'm going to stop sharing, and I think James will open it up to any questions.
Yeah, Kevin, thanks for that presentation.